So as odd as it may seem, there's a theory of counting. Right? And I remember one of my favorite classes I took in college was about number theory, and it dealt with codes and like the math that they use for like encryption and stuff like that. So these types of questions of like how many different ways can I mix these things it falls into the thought of counting theory, or the principle of counting. Okay? And so what's really going to come down to, the math is simple. At any point, all we're going to be doing today, guys, is multiplying. It's the only math we're going to be doing is just multiplying. Okay? So your calculator can do all that for you. You have to understand the situations. So these are really just reading problems. Can you read them and make sense of what's happening? Here's what you guys need to make sure you're focusing on. Okay. So, essential question today: how many different four-digit PIN codes are there? Right. So when you go in and pick your PIN for your phone, if you just do a 4-digit code, how many different options are there for that? So how do you figure that out? All right. So every time you guys were looking at making a choice there for, which shirt to wear, which pair of pants to wear, which belt to wear, which hat to wear, that's called an event. Every opportunity to make a choice, or every chance to make a choice is an event. Okay? Within that event, there were choices. So, hey, pick a shirt. You have 3 choices. Hey, pick a pair of pants. You have 4 choices. Pick a belt. You have 2 choices. Pick a hat. You have 2 choices. Okay? So you have opportunities to make choice. Okay? You have time, like when do I get to make a choice? Like that, you have to identify those as events. How many choices do I get to make? How many times do I get to make a choice? And then within that choice, how many different ways can I choose it? Okay. So we keep using this word choose and choice over and over again, and it gets really kind of jumbled in your head, and you have to be really, really clear about what's an event versus how many choices are within that event as you're trying to pull these problems apart, these word problems apart. What this could be like, so when we say, every time we do that was an event, and that those events were independent of each other. If we take style out of it, right, that things don't have to match or anything like that. The shirt I choose has no bearing on the pants I choose, has no bearing on the belt I choose, has no bearing on the hat I choose. They're completely independent of each other. Okay? In the same way that if I flipped a coin 5 times, the coin doesn't know what it landed on the time before. It's not going to change what does next. And same thing with if I roll a die. It has no memory of what happened. So those are independent events. When I roll a die, it's completely independent of everything that's happened before that. Okay? So independent events, it doesn't matter what happened before, you still have the same number of choices as you did before. Okay? So when I go to roll that die, I could get a 3. Next time, I can get a 3 again, or I could get a 4. There's still 6 possible things that could happen. Okay? If I roll it 12 times, each time there's 6 things that could happen. Okay? That's the idea of what it means to be independent. So if that's what it means to be independent, what does it mean to be dependent? What are dependent events? What are dependent events? Or what's an example that you might be able to think of dependent events? Okay, so something that changes in response to something else. Reyes, like what? Keep the turn. Something that changes because something else because something happened. What could you do that could be a dependent event? Say again, right? Okay. So how can we turn that into a situation? So Ray said, you eat at a bad restaurant, you don't go there again. How can we turn that into a situation like picking out clothes, or flipping a die, or rolling a die, flipping a coin? How do we turn that into like events are opportunities to make choice, and then within that event there are choices. How could we create an event based around you were talking about eating in a restaurant? An opportunity to make choice is an event. How do we create an event around eating at a restaurant? So you've got a list of 6 restaurants. So the event is choosing one, right? And then now all of a sudden, one of them is bad. So the next time you go to choose, you had 6, now you've only got 5 because you don't want to go there again. So you just create a dependency. So it could be a bad restaurant, or maybe just say, I don't want to eat the same place next time, right? It doesn't have to be, it has to be bad. It's just that I don't want to go to the same restaurant again. I want to go to a new place, right? There's dependency. Right? What I did the first time affects what I did this year. That's another way. What's something else that could be dependent? Another example of something being dependent. That was good, right? Okay. Can we take that number away though? So people are saying like, if we re-roll and they got the same number again, like, can we actually change the dice so it doesn't roll on that number again? Yeah, probably not. Right? That'd almost become like more of like, well, that sounds to me as like a recording issue. Like you're just not going to record the number again, but not that it didn't land on it. I don't know. Pick a card, any card. Here, Matt, draw Jack out of the deck. How many choices did you have the first time? 52, right?
Yep.
So Matt's pulled a card out of the deck and didn't get a Jack, whatever. What happens the next time? Grant, pull a card out of the deck. Do you have the same choice that Matt had? Why not? Because he took one, right? So if Matt takes the card and then Grant has less choices the next time, we've just created dependency. What Matt did is going to change what's going to happen. What's Grant's choices, right? And then if I went to Andrew after that, then there's different. How can we take that dependency and turn it back into independency? The card back in, right? Did you get Jack? Nope. Oh, put it back in. I'm going to the next person. Now it's independent again. Okay. You guys, you see those bags with marbles in them. Like, all right, pull out a marble, see what you get, right? Well, if you keep the marble, now all of a sudden there's dependency. What do you pull out the next time? When you pull out the next time, you're keeping them. Versus independent, put the marble back in. It's just like the system is reset. Okay? It has no memory if you put the marble back in. It has no memory if the card's back in. Okay? It has no memory if we just, that restaurant sucked. Well, you keep the same list. You pass it to the next person. They don't know which restaurant sucked. Like, there's no memory there, right? So how do we create memory within the system? Okay? How do we create change within the system? That creates dependency. But all this stuff, guys, is within the context of the situation. It's not going to say, hey, it's dependent, or it's, hey, it's independent. You have to be able to read that and say, oh, this is going to change things, or, oh, no, system's reset. This isn't going to change anything. So that's the part what we really need to be picking apart today, guys, is how many opportunities for choice do we have? And then how many choices do we have each time we get to go make a choice? Okay? We had 4 times we got to make choices here. I get to pick a shirt. I get to pick a pair of pants. I get to pick a belt. I get to pick a hat. There was 4 events. How many choices do we have each time? Right? 4, 3, 2, 2. Okay? That's what we have to worry about. The math is just multiplication. We don't need to worry about the math. How do we figure out how many numbers we're supposed to be multiplying and which numbers to multiply? That's what we need to worry about. Okay? So that's what we need to practice. So if you don't want to write that whole example down, what you need to know for sure to make sense of this is that there's a 5-course meal. There's 3 soups, 2 salads, 6 main dishes, 4 sides, 4 desserts. And the question is the number of different 5-course meals. Okay? So if you don't want to write the whole thing down, that's fine, but that's what you need to know in order to make sense of this problem. So when you go back and look at it later, you're not just like, oh, what was this? We'll break it down to 2 questions, guys. How many events are there? And how many choices are there within each event? Okay? Those are the 2 questions you need to be asking yourself to make sense of these problems. How many events are there? How many choices are there within each event? How many opportunities do you have to make a choice with this problem? Right? 5? All right, the waiter's going to come up and ask you 5 questions, right? Each time you get to make a choice. So there's 5 events. So identifying that, which means we're going to have 5 numbers we need to multiply. Something times something times something times something. Okay. The first thing we get to choose from has how many choices? 3 suits, right? Second thing we get to choose from has how many choices? 2. So on and so forth, right? 6, 4, 4. 3 times 2 is 6, times 6 is 32, times 4 is 144, 400, 560, 576, is that right? So 576 different meals. Again, not accounting for taste, not accounting that I want my soup to complement my salad or whatever. Just purely how many different things can I make? Okay. 2 questions. How many events are there? How many choices are there within each event? Pulling that all out of the context of the problem. Okay. Here we're looking at, there's the essential question, right? How many different 4-digit PIN codes are there? So that first time you go to set up your phone, right, you got to pick your password, the PIN. How many codes do you have option of making, right? Or somebody gives you their phone and said, hey, guess my PIN, right? How many different guesses could you possibly make? Okay. So 2 questions. How many events are there? How many options, how many choices in each event? So how many events are there? Okay, 4. Why is it 4? Okay. You're setting your PIN. You have to pick the first number, choice. You have to pick the second number, choice. Pick the third number, choice. Pick the fourth number, choice. So there's 4 numbers we need to multiply. How many digits are there? 10 digits. 0 through 9 is 10. So that first time you have 10 choices. The second time you have 10 choices. The third time you have 10 choices. Fourth time you have 10 choices. How many codes are there? What's 10 to the 4th power? And one with 4 zeros after it. So purely random sense, right? If you just had to guess random numbers, or you picked random numbers, there would be 10,000 ways to arrange those. But psychologists know that people don't just pick random numbers. Okay? They have like patterns, like certain things about the number so that they can remember them. You're not going to remember a purely random number very well. So hackers and stuff study that psychology to limit that. Know that chances are you're not going to do a random. There's some sort of pattern within your that will actually change how many guesses they would need to make. Mathematically, it's purely random and be 10,000. So what if we start adding little caveats onto the problem? Hey, you're not allowed to repeat numbers now. So how many events are there? Still 4. Yep. Still have to pick 4 numbers. A number times another number times another number times another. That first number you pick, how many choices do you have? 10. What about the second number you pick? 9. You can't pick the same number you already picked. Second time? Or third time, sorry. What's next? 8, and then 7. Only have so many choices now, right? What's that give us, Grant? What's that give us? Sorry, say again. Thank you. So just by saying, if somebody gave you their phone and said, "Hey, guess my PIN," I'll just give you a hint. There's no repeats. Well, you cut the codes in half. All right, and the last one, there's a little bit. I think there's a little bit of unclarity in it. This will happen sometimes. So we just need to, I guess, kind of a consensus, or we can look at both. So it says, what if the first and last digit can't or must be the same? What it doesn't say is like how the first digit can compare to the second digit. Like, can they repeat or not? It doesn't say that. So we could, look at doing both. So it's just something that can happen sometimes, like when they don't say something, you're not sure if it's implied or not. It just says the first and last digit must be the same. It doesn't say anything about anything else. So maybe that means that we are allowed to repeat numbers. Okay. Like the second number could be the same as the first number. It doesn't say that, so maybe it could be. So with repeats, still 4 events. That first time we could pick 10 from 10 numbers. If we're allowed to repeat, we could pick the same number again. So that means we could pick 10 numbers again. Still allowed to repeat if we want, so we could pick 10 numbers again. But the last number has to be the same as the first. How many choices do we have? 1. Yeah, right. Whatever it was, I have to pick it again. Right? It was already decided a while ago, right? So now there's only 1,000 codes. So if somebody tells you, "Hey, guess my PIN," I'll just tell you the first and last number are the same. Just cut the choices to 1/10, right? 1,000 instead of 10,000. So see how you limit yourself by adding things like that into your PIN. Like, so much less safety there. And then what if there aren't repeats? What if you can't repeat a number? Sorry. So the second can't be the same as the first. The third can't be the same as the second or the first. Like the first rule is still there. The first and last one are going to be the same. That first time we go, we have 10 choices. Then we only have 9. We only have 8. And then we only have 1. 9 times 8 is 72. Times 10 is 720. Your first and last number are the same, and then the other two are different, then there must only be 720 possible combinations for that. You guys need to be thinking about how many times do I get to make a choice, and how many choices do I have each time. So when we add a caveat like that, we're creating dependency. So this is an independent situation. This is a dependent situation. This is a dependency. Right, you're limiting choices. But it's not going to say that. You've got to read the context. I'd like you guys to try these 2/3 problems. I'll give you guys about 5-6 minutes to do that. Just want you to try it out, test your thinking, okay? See how you're making sense of it, what we need to fix, okay? Just try them out. Give it about 20 after, and we'll talk. Ruthie, what'd you do on that first one?
The first one, I did 6 events, and then I put 2 for them because like 6 to the power of 2 is 36. So
You put 2 6 times?
yeah.
So that would be 2 to the power 6, not 6 to the power 2.
Oh. Oh, okay.
So you're saying you meant to do this?
Yeah.
Okay. All right. So 6 times 6 is 36. Grant, what'd you do? Yep. Same thing? Okay. Colby, what'd you do for the first one? First one. Six times six. Okay. What's that equal to? 600. Okay. Tiger, what'd you do?
6 to the power of 2.
6. Okay. Victoria?
I did the same, the 6 times 6.
Maddie?
I did it 6 times 5 times 4 times 3 times 2 times 1.
Like that?
Yeah.
What'd you get?
620.
720?
Mm-hmm.
Okay. Wes, what'd you do? 6 times 6. Piper, what'd you do? Caleb? Okay. Matt?
I did 6 times 6.
Okay. Claire? Okay. All right. So we got 3 different answers here. How many opportunities are there for someone to make a choice? 6. So which of these can't be right? There's not 2 events. There's 6 events. Okay? There's 6 times somebody goes up and picks a seat. There should be 6 opportunities for a person to make a choice. 6 events. Okay. First person goes up, makes a choice. How many choices do they have? They go up to the car. How many choices do they have? 6. Second person goes up to the car. How many choices do they have? Where are they going to sit? 5. Why? C got taken. So these events are what? Dependent. Did it say that anywhere there? No. You have to read the context. Okay? How many different choices, how many different opportunities are there for a choice to be made? 6. That first time, how many choices does that person have? Second time, how many choices does that person have? Right? It's changing. Okay? Seats keep getting taken. Okay? So there's 720 ways to fill that car. Okay? You've got to read the context. It's really easy to lose those things. Okay? 720 ways. And that's where the math isn't hard because you're not doing it. Right? You're just typing in your calculator. But how do you read it? How do you make sense of what's going on? Okay? And that difference between opportunities to make a choice and choices that you have. Okay? Matt, what'd you do for the first one here on the purple?
I was a little confused, but I started it with 4 numbers.
Okay.
I did 4 events.
Okay, so 4 events for numbers, 10 each time.
And then for numbers, I did 4 events.
26 each time. Okay.
Yeah.
And that's what was it, like 4 billion something? So a couple of you guys did that, right? I mean, plus, like it's 4 billion plus like combinations there. Okay. You have to pick 8 things. There's 8 times you can make a choice. There's no restrictions on anything, so that means all these events are independent. Okay, so I could 10, 10, 10, 10, 10, right? And then pick letters, 26, 27. There you go. That's how it works. Okay. All of a sudden, we add a restriction onto it. Okay, and we've got dependent events. Right? It's 10, it's 9, it's 8, it's 7. Okay. 26, 25. I think I saw you guys all here that were doing this. I think you're doing fine. Okay, not doing around 1 billion. Okay. So that creates dependency. Okay. Why don't you guys come in